In this chapter, we're going to look at two-dimensional motion. Two-dimensional motion. Two-dimensional motion means motion in a plane. This is motion in a plane. If you remember, one-dimensional motion was motion in a straight line. This is motion in a plane. But we're going to start by discussing the motion variables first. So let's look at the motion variables. We're going to need to discuss two-dimensional motion. Okay, as we did before, we're going to start with position vector. Position vector, we're going to use capital R to represent it. Okay, this is the vector whose tail is the origin and whose head is as the location of the particle. Let's say the particle is located over here. The position vector of this particle is this vector. The vector whose tail is the origin and whose head is the location of the particle. So you can say this is the vector whose tail is at the origin and whose head is as the location of the particle. Whose head is at the location of the particle. Location of the particle. Okay. Now suppose the position of this particle, let's say xy. All right. So what that means is this one over here is x, and this one over here is y. Remember, it's a position vector, so that tells you the x component of the position vector is simply the x coordinate, and the y component of the position vector is simply the y coordinate of the particle. So we have the following: Rx simply equals x, and Ry simply equals the y coordinate. So the particle is located as the point xy, then the x component of the position vector is simply the x coordinate, and the y component of the position vector is simply the y coordinate. Okay, now as you know, we can write any vector as follows: R equals its x component in the I direction plus its y component in the j direction. Therefore, that means the position vector can be written as simply x in the I direction plus y in the j direction. Okay. Next, we're going to look at the displacement vector. Displacement vector. We're going to use delta r, or change in r, to represent it. So this is basically change in the position of a particle. Okay, this is change in position vector. Okay, so that means mathematically delta r is simply the final position vector minus the initial position vector. Now suppose the location of the final position is xf, yf, and the location of the initial position vector is xi, yi. So it follows that delta r equals rf minus ri, which means this is xf in the I direction plus yf in in the j direction minus xi in the I direction plus yi in the j direction. All right, so we subtract I with I, j with j, so we get the following. This is x final minus x initial in the I direction, and then plus y final minus y initial in the j direction. Okay, this is change in x in the I direction plus change in y in the j direction. Okay, so we can say delta r equals delta x in the I plus delta y in the j, or xf minus xi in the I direction plus yf minus yi in the j direction. Okay. Now if you want magnitude direction, then delta r would be square root of delta x squared plus delta y squared, and then of course the direction would be tan inverse of delta y over delta x. Of course we would add 180 degree if delta x is less than 0. Alright, now let's look at the geometric meaning of change in position vector. Okay, suppose let's say a particle is displaced from this location, so that would be our initial position vector, and let's say it's displaced to this location, and that would be our final position vector. So we've got rf over here, we've got ri over here. Okay, so we're looking for rf minus ri, right? So delta r is final position vector minus initial position vector, but this can be written as the final position vector plus the negative of the initial position vector, right? So if this is ri, is negative ri goes this way. Okay, you connected the head of this, you see this will be negative ri. So this is delta r, which is the same as this vector over here. So this is delta r. Okay, this vector is delta r. So you see, graphically, the displacement vector is the vector whose tail is at the tip of the initial position vector, and his head is the head of the final position vector. Okay, and also you can see that this is x final, this is x initial. For this one over here is delta x. Okay, this is y initial, this is y final. So you can see also this one over here is also delta y. So it's delta x in the I direction plus delta y in the j direction. So we can say that graphically, the displacement vector, is the vector whose tail is at the initial location, and whose head is at the final location, whose head is at the final location. So the displacement vector is simply the vector that connects the initial location and the final location. So next we're going to look at average velocity. We're going to use v vector average like this. Okay, this is simply change in displacement per a unit time. This is change, change in position vector or displacement per unit vector. This is displacement per a unit time, or change in position per a unit time. Okay, so that means mathematically we can write this vector as delta r as displacement divided by the time taken. Okay, but remember delta r is delta x in the I direction plus delta y in the j direction divided by the time taken. So we have the following formula for the average velocity is delta x by delta t in the I direction, and then delta y by delta t in the j direction. Okay, so this is the x component of the average velocity, this is the y component of the average velocity. So you can say v power x equals delta x by delta t, that is the x component of the average velocity, and the y component of the average velocity also equals delta y by delta t, right? So that is how we write average velocity. It is displacement per a unit time. Next, we're going to look at instantaneous velocity. Instantaneous velocity. So we're going to use this v vector for this one. Okay. This you can say is velocity at a given instant of time, but also you can say it's average velocity evaluated a very, very small interval of time, or at infinitesimally small interval of time. This is, you can say, average velocity evaluated at a very, very small interval of time. Okay, so we start with the definition of the average velocity, which is delta r by delta t, and then if you push delta t to 0, that is, if you evaluate this at a very, very small interval of time, actually infinitesimally small interval of time, it becomes instantaneous velocity. And there's a way of writing that in calculus. We say the limit of this expression as delta t approaches 0 is what we call instantaneous velocity. Okay, if this average velocity is evaluated as delta t approaches 0, it becomes instantaneous velocity. Okay, but you know, this is a definition for something in calculus. Okay, this is a definition for the derivative of the position vector with respect to time. So we can say this is the derivative of the position vector with respect to time. This is the definition of a derivative. Now let's write in terms of components. So v would be the limit as delta t approaches 0 of the following: delta x by delta t in the I direction plus delta y by delta t in the j direction. Okay, so we take the limit of both terms. This becomes the limit of delta t approach of this one is the derivative of position with respect to time in the I direction. Okay, and that becomes the derivative of the position y with respect to time in the j direction. Okay, so that is the expression for instantaneous velocity. Okay, so we see that the x component of the velocity is the derivative of the x component of the position vector, and vy, or the y component of the velocity, is the derivative of the y component of the position vector with respect to time. Okay, so that's how we evaluate instantaneous velocity. It is a derivative of position vector with respect to time. And then we're going to look at average acceleration. Average acceleration, we're going to use a vector average. Okay, this is defined to be change in velocity per a unit time. This is change in velocity per a unit time. Okay, let's write that mathematically. This definition is written as the average of the acceleration is change in velocity divided by the time taken for this change. Okay, but we know that delta v is v final minus v initial divided by delta t. Okay, Now if you write it in terms of components, this will be delta Vx in the I direction plus the y component of the change in the j direction divided by delta t divided by delta t. Okay, so that's it. So the average acceleration, the x component of the average acceleration is delta Vx by delta t, and the y component is the change in the y component of the velocity divided by the time taken. So we have the following. The x component of the average acceleration is the change in the x components of the velocity, and well, this means Vfx minus Vix divided by delta t. Okay, the x component of the final velocity minus the x component of the initial velocity, and then Ay is delta Vy divided by delta t, which means Vfy, the y component of the final velocity, minus the y component of the initial velocity. Okay, so that's how we calculate the x component and y component of the average acceleration. Okay, and this would be general definitions in terms of vectors. All right, now let's look at instantaneous acceleration. Instantaneous acceleration. We're going to use A for this one. Okay, this is acceleration at a given instant of time, but we can also say it is average acceleration evaluated at a very, very small interval of time. So we can say this is average acceleration evaluated at a very, very, or infinitesimally in the language of calculus, interval of time. Okay, so that means we start with the definition of average velocity, which is delta V divided by delta t, and then when this is evaluated and the limiting value as delta t approaches 0, that becomes instantaneous acceleration. Okay, but as you know, this is also the definition of a derivative in calculus, so you can say acceleration is the derivative of the velocity with respect to time. Okay, now let's write this in terms of components. The average acceleration will be delta Vx by delta t in the I direction, and then the change in the y component of the velocity divided by delta t in the j direction, right? And then we take the limit of this expression as delta t approaches 0. We get the following. We get the limit of delta Vx by delta t as delta t approaches 0 in the I direction, and then plus the limit as delta t approaches 0 of this ratio delta Vy by delta dt, delta t in the j direction. Okay, so this is the derivative of the x component of the velocity, and this is the derivative of the y component of the velocity. So we can say that the acceleration, this is of course A over here, so the acceleration is the derivative of the x component of the velocity with respect to time in the I direction, plus the derivative of the y component of the velocity with respect to time in the j direction. Okay, so this is the component form of the instantaneous acceleration. Now remember, Vx equals the derivative of x with respect to time, and Vy equals the derivative of y with respect to time. Okay, so if you substitute this for this over here, we get acceleration equals the derivative with respect to time. You see Vx equals this one of dx by dt in the I direction, and then we got the derivative with respect to time of Vy. Vy equals this one, so you get dy by dt in the j direction. Okay, but if you remember in calculus, this is the second derivative of position with respect to time. This is second derivative of x with respect to time. This is second derivative of y with respect to time. So we have the following expression for acceleration in terms of position. It is the second derivative of x with respect to time in the I direction, and the second derivative of y with respect to time in the j direction. So we can also write it in terms of position like this. It's the second derivative of position vector with respect to time. Or you can say a equals the second derivative of position vector with respect to time. Okay, so these are the motion variables we'll need. We don't need to go beyond acceleration because our goal is to find the relationship between force and motion, and the relationship depends on acceleration, so we don't have to go beyond acceleration. All right, so before we go any further, let's look at an example. Okay, let's say, suppose the position vector of a particle varies with time according to the equation. Let's say this r, the position vector, is a function of time, and let's say it is maybe 2t squared plus, let's say 3t plus 1 in the I direction, and then maybe 4t plus 3 in the j direction. Okay, so now we're going to ask some questions. A, let's say where is the particle, let's say after 10 seconds. Okay, so where is position, right? So we're looking for r. We're looking for the position vector at t equals 10. Okay, at t equals 10. So all we have to do is calculate, put 10 in instead of t in these equations. Okay, so r t equals 10, this is question mark, at t equals 10 will simply be 2 times 10 squared plus 3 plus 1 in the direction, and then we got 4 times 10 plus 3 in the j direction. Okay, so we got 230, oh, there's times 10 over here, sorry. So that is 231 in the I direction plus 43 in the j direction, maybe meters. Okay. B, let's calculate displacement. Calculate the displacement of the particle, let's say in the first 2 seconds, let's say. So this is between t equals 0 and t equals 2 seconds, okay, in the first 2 seconds. So what that means is our initial position vector is position vector at t equals 0, and our final position vector is position at t equals 2. Okay, and our displacement vector is simply final position vector minus initial position vector. Okay, so delta r is the position vector at t equals 2 minus the position vector at t equals 0. Okay, so we have to calculate these two position vectors, and then we subtract them. Okay, so this one will be 2 times 2 squared plus 3 times 2 I guess plus 1. Okay, that's in the I direction. And the second one is 4 times 2 plus 3 in the j direction. Okay, so this is our first vector. Okay, the position vector at t equals 2, and then we're going to subtract the position vector at t equals 0. Okay, I mean t equals 0 at 2 squared plus 3 times 0 plus 1 in the I direction, and then plus 4 times 0 plus 3 in the j direction. Okay, so what do we have? This one is 4 times 2, 8. 8 plus 6, 14. 15 in the I. And this one is 4 times 2, 8 plus 3 plus 13 in the j. And then we're going to subtract this. This is just 1 in the I. Okay, and this is 4 times 0 over here plus 3 in the j. Okay, so the position vector is 15 minus 1, 14 in the I, and then 13 minus 3, 10 in the j. Okay, so that will be the displacement in the first 2 seconds, maybe meters over here. All right, now number 3, let's calculate the average velocity let's say in the first 2 seconds. So we're looking for this variable over here, the average velocity in the first 2 seconds. Okay, that's the question mark over here. All right, so by definition, average velocity is displacement divided by time taken. Okay, so we have already calculated the displacement in the first 2 seconds in part 2. Okay, so we already know delta r for this is the same displacement. So this is 14 in the I plus 10 in the j meters, and of course the time taken is 2 seconds. Okay, 2 seconds. So the average velocity in this case is 14 in the I plus 10 in the j meters divided by 2 seconds. Okay, so we get 7 in the I plus 5 in the j meters per second. Okay, number 4, now let's calculate the instantaneous velocity. Calculate the instantaneous velocity, maybe let's say after 5 seconds. 5 seconds. Okay, so the question is calculate v at t equals 5. That's the question. Okay, now we have position vector as a function of time, but first we need to obtain velocity as a function of time to solve this problem. Okay, so we know that velocity is the derivative of position vector with respect to time. Okay, but we are told that the position vector is right over here, 2t squared. This is 2t squared plus 3t plus 1 in the I direction, and then plus 4t plus 3 in the j direction. Okay, so we have to evaluate this derivative, and that gives us the expression for the velocity as a function of time. So the velocity equals the derivative of this one is 4t, and the derivative of this one is 3, so that's in the I direction, and then plus 4 in the j direction. Okay, now we can solve for the velocity at t equals 5. So the velocity at t equals 5 equals 4 times 5 plus 3 in the I direction plus 4 in the j direction. Okay, so that's 23 in the I direction plus 4 in the j direction. So that is the velocity or instantaneous velocity after 5 seconds. Okay, now let's calculate average acceleration. Calculate the average acceleration between, let's say, t equals 1 and t equals 3 seconds. Okay, so we're looking for the following: average acceleration between t equals 1 and t equals 3. Now, by definition, average acceleration is delta v divided by delta t. Okay, that is v final minus v initial divided by t final minus t initial. Okay, now according to this problem, v initial is the velocity at t equals 1, and v final is the velocity at t equals 3. Okay, so we can say in this case the average velocity is the velocity at t equals 3 minus the velocity at t equals 1 divided by t final, which is 3 minus 1. So it's basically the change in velocity divided by the time taken. All right, but we know the expression for the velocity. Okay, the velocity we saw in the previous problem is 4t plus 3 in the I direction plus 4 in the j direction. So that means v at t equals 3 equals that is 12 plus 3, 15 in the I plus 4 in the j. Okay, and the velocity at t equals 1 is 4 times 1 plus 3, that is 7 in the I direction, and then plus 4 in the j direction. Okay, therefore the acceleration is v at t equals 3, which is 15 in the I plus 4 in the j, minus the velocity at t equals 1, which is 7 in the I plus 4 in the j, divided by the time taken, which is 2. 3 minus 1, 2. Okay, so you see 15i minus 7i is 8 in the I, and 4j minus 4j is 0. Okay, divide that by 2, we get 4 in the I meters per second square. Okay, so this is the average acceleration in this interval of time. Okay, finally we're going to look at instantaneous acceleration. Let's say it's number 6. Calculate the instantaneous acceleration, let's say after 4 seconds. Okay, so the question is to calculate the acceleration at t equals 4. Okay, that's the question. Now we have an expression for the velocity as a function of time, so we're going to have to find an expression for the acceleration as a function of time first. Now acceleration is the derivative of velocity with respect to time, right? But we just saw in the first section that velocity is 4t plus 3 in the I direction plus 4 in the j direction. Okay, so we take the derivative of this. Acceleration equals the derivative of 4t plus 3 in the I direction plus 4 in the j direction. Okay, so this is simply 4 in the I direction. The derivative of a constant is 0. Okay, so the acceleration is always a constant. That's at any time again before. So you've got acceleration at t equals 4 is simply 4 in the I. It's independent on time. It's a constant. All right, so these are the 5 motion variables. Now we're going to specialize to a special kind of motion. It's called uniformly accelerated motion, as we did in the case of one-dimensional motion. So let's look at uniformly accelerated motion. Okay, as we saw in the case of one-dimensional motion, this simply means motion with a constant acceleration, or motion where the velocity is changing at a constant rate. So this implies motion with a constant acceleration. But remember, acceleration can be written in component form like this: the x component in the I direction plus the y component in the j direction. So if the acceleration is a constant, both components must be constant. So this implies the x component of the acceleration is a constant, and the y component of the acceleration is constant. Okay, so a uniformly accelerated motion is motion where the acceleration is a constant, or a motion where the velocity is changing at a constant rate. Okay, now the x motion and the y motion are independent of each other. What that means is acceleration in the x direction does not affect what happens in the y direction, and acceleration in the y direction does not affect what happens in the x direction. Okay, so x motion and y motion are independent of each other because they're perpendicular to each other. Independent of each other. It's just like y, I and j are independent. It's because they're perpendicular to each other. Okay, are independent of each other. Okay, what happens along x doesn't affect what happens along y. This acceleration along x does not affect the motion in the y direction. Acceleration along the y direction does not affect what happens along the x direction. So what this implies is both motions could be treated separately. Both motions can be treated separately. So instead of dealing with a two-dimensional motion, we can deal with two one-dimensional motions. That is, one-dimensional motion along x and one-dimensional motion along y. Okay, but we already know the formulas for uniformly accelerated motion in a straight line or in one dimension, right? So we're going to separate the x motion and the y motion, and we'll just write the formulas for a uniformly accelerated motion for both the x and the y motions. Okay, so we're going to separate them into two. Let's put the x motion formulas over here, x motion, and then let's put the y motion formulas over here. So the only difference with the previous problem is now we're going to use the x components on this side. We're going to write the y components on this side. This side relates the x components, and this side relates the y components, because the x motion and the y motion are independent. Okay, so the first one be vx equals vix plus x component acceleration times time, and then we've got delta x equals vixt plus half ax t squared, and then we've got vfx squared equals vix squared plus 2 times ax times time, or times delta x, I'm sorry, times delta x. And then we have delta x equals Vix plus Vfx over 2 times t, and we have the same equations for the y component. We have Vfy equals Viy plus ay times t, and then we have delta y equals Viyt plus half ay t squared, and then we have Vfy squared equals Viy squared plus 2ay times delta y, and then we have delta y equals Viy plus Vfy over 2 times time. Okay, so these are the one-dimensional motion equations for the motion in the x direction, and these are the one-dimensional motion equations for the motion in the y direction. All right, now we can write this equation as a vector form. Let's try to do that. Maybe first let me put this in a box. These are the equations for a uniformly accelerated motion. Now the final velocity equals Vfx in the I direction plus Vfy in the j direction. Okay, but we just saw that Vfx equals Vix plus Ax t in the I direction, and this one equals Viy plus Ay t in the j direction. Okay, now we can write this like this. We can put these two together. We've got Vix in the I direction plus Viy in the j direction. Okay, we can do the same thing for the acceleration. We have Ax in the I direction, Ay in the j direction. So we've got Ax in the I direction, Ay in the j direction times time. Okay, but remember, this is the initial velocity Vi, and this is the acceleration A. Okay, so we have the following vector equation: Vf equals Vi plus acceleration times time. Okay, so this is how you write it vectorially. All right, now remember, from one-dimensional motion we have only two independent equations over here. These are dependent equations included to make solving the problems easier, but we have only two independent equations. So let's express this one in vector form. We already did this one. We're going to do the delta x first. So the displacement vector delta r is delta x in the I direction plus delta y in the j direction. Okay, but as you can see from here, delta x equals this equals delta x equals Vix plus half Ax t squared in the I direction, and then for the y we have the same thing, Viy plus half Ay t squared. Okay, so now we can organize this equation. Let's put these two together. This is j, this is I, so you've got Vix in the I plus Viy in the j. Okay, and then we can do the same thing for the acceleration. We have Ax in the I plus Ay in the j, and then we've got t squared over here. Okay, but you see this one is there's t over here. I'm sorry, there's t over here. So this would be Vit. Okay, this expression would be half a t squared. Okay, so vectorially this equation could be combined as delta r equals vector it plus half a t squared. Okay, so this is the vector form equation for the position vector. Okay, now let's look at an example. Let's say the initial velocity of a particle, let's say, is maybe 2 in the I, maybe 3 in the J meters per second. Okay, and it's moving with an acceleration of, it's moving with an acceleration of, let's say, maybe 4 in the I, maybe let's say 5 in the J meters per second square. Okay, the question is A, let's say calculate its velocity maybe after 5 seconds, after 5 seconds. Okay, so we're being asked it for the velocity at t equals 5. Okay, so we have the velocity at t equals 0. This is our initial velocity, and the velocity at 5 seconds would be our final velocity. Okay, so that's what we have. Vi, as the initial velocity, is 2 in the I plus 3 in the J. This is 2 in the I plus 3 in the J meters per second, and we're told the acceleration, the constant acceleration, is 4 in the I plus 5 in the J. 4 in the I plus 5 in the J meters per second square. The question is to obtain V final, which is the velocity at t equals 5. Okay, so we're going to use the following equation. V final, or V at t equals 5, equals Vi plus acceleration times time. Okay, so our time obviously is 5 seconds. All right, so this is, we have 2 in the I plus 3 in the J for the initial velocity. For the acceleration, we have 4 in the I plus 5 in the J, and the time taken is 5. Okay, so this would be 2 in the I plus 3 in the J, that we multiply by 10, plus 20 in the I plus 25 in the J. Okay, so we connect the i's with i's, so 2i plus 20i is 22 in the I direction, then we got 3 in the J, 25 in the J, plus 28 in the J. So this is the velocity after 5 seconds meters per second. Okay, B, let's say maybe calculate its displacement, again after 5 seconds. Okay, so we want to obtain its displacement at t equals 5. Okay, so we're going to use the following formula. Delta R equals VIT plus half a t squared. Okay, so vectors. All right, the initial vector for the velocity is 2i plus 3j, and the time is 5, plus half. The acceleration is 4 in the I plus 5 in the J, and the time is 5 squared. Okay, so you get 5 times 2, 10 in the I plus 15 in the J. Okay, and then we have 4 divided by 2 times 250. This is 50 in the I, and then for this one we have 125, and then divide by 2, which is I think 62.5 in the J direction. Okay, 125 divided by 2. All right, and then we add the i's with the i's. We have 10i plus 50i, that's 60 in the I, and J 15 plus 6.7 is 77.5 in the J. So this would be the displacement after 5 seconds.